Hi, I'm J Wildberger. In today's video, we are going to look at geometry with a general dot product. So we're extending our understanding of metrical geometry, metrical planar geometry, to a much wider arena now, where we're going much beyond the familiar blue, red, and green geometries that we've been talking about in the context of chromogeometry. So the blue geometry is the familiar Euclidean one given by the familiar dot product. Then there's this red variant with a minus sign instead of a plus sign. And then this other relativistic one, another variant called the green one with this particular dot product. And each one of these dot products is naturally associated with a 2 by 2 symmetric matrix in the context of linear algebra. Great, so now we want to look at a more general situation where we have the dot product of the vectors A, B, and C, D given by this number here, determined by a symmetric 2 by 2 matrix of a rather general kind with entries L, M, M, and N. So we take this vector AB, we multiply by the 2 by 2 matrix, that one there, and then the column vector CD, and we get a number, and that's the dot product between these two vectors. Being able to do metrical geometry in this very general context is enormously empowering. It gives us all kinds of new tools to understand traditional classical things and also to go much further, into the relativistic setting, very important for physics. So this is going to be really bread and butter stuff for 21st century physicists. But also it just allows us to understand a lot of things in mathematics from a more broader point of view. We're going to be especially interested in applications to classical triangle geometry. And we'll see that having this point of view allows us to really see a lot of things in a new light. So today let's have a look at an introduction to understanding this very general kind of planar metrical geometry. So to really get to grips with this, let's have a good look at an explicit concrete example. We're going to introduce the following dot product. So U is the vector AB, V is the vector CD, and now here is the dot product that we're going to be considering. U dot V is this number right here. Let's have a look at it. 3/8 AC minus 1/4 AD minus 1/4 BC plus 1/2 BD. Notice that these terms here are all quadratic terms obtained by taking one of these terms and multiplying it by one of those terms. So when you just look at it as a function of U, or A and B, it's linear in A and B. And if you just look at it as a function of V, or C and D, then it's linear in C and D. So it's linear both from the U point of view and from the V point of view. That's what we mean by it's bilinear. This thing here can also be written in matrix form using this 2 by 2 matrix, and you can kind of see where the entries come from. They're just these various coefficients. So the vector AB, the vector CD and transposed, and here we have 3/8 minus 1/4 minus 1/4 and 1/2. And we could call this matrix M. That's then a symmetric 2 by 2 matrix that's encoding the dot product in matrix form like this, the vector U times the matrix M times the transpose of V. And we note that this actually is symmetric because these two entries agree. The coefficient of AD, the coefficient of BC are equal. The other important thing to observe about this matrix M that's encoding our dot product is its determinant. The determinant is obtained by taking this entry times this entry and subtracting the product of this entry times this entry. That's a total of 1/8. And the most important aspect of that number is that it is not 0. So this is a non-zero determinant matrix. Or in linear algebra language, it's an invertible matrix. It means that this matrix is invertible. It means that it has an inverse matrix and has other important properties. But in particular, that number 1/8 is something that will figure in the geometry associated to this dot product. So in today's lecture, we're going to look at what it actually means to examine geometry from the point of view of this particular metrical structure. This kind of geometry can be thought of in terms of a bilinear form, as we've been doing, a dot product, or also as a quadratic form. These are sort of two different ways of looking at essentially the same thing. So in this context, the quadratic form is what you get when you take the dot product and you take the vector dotted with itself. So both entries are the same vector. And we could call that Q. So Q of a vector U is then U times M times U transpose. Or if you like, U dot U. Now explicitly, in terms of coordinates, this Q of AB is 3/8 of A squared minus 1/2 AB plus 1/2 B squared. The two minus a quarters here combine to just give a single minus a half. And this is really defining a quadrant. Exactly parallel to the Euclidean quadrants, but now it's a more general kind of quadrant. But it still plays the same role. Okay, so this expression defines something very geometrical, especially when we set it equal to 1 and consider the corresponding unit circle. The unit circle is then Q of U equals 1, or explicitly this equation here, 3/8 of x squared minus 1/2 xy plus 1/2 y squared equals 1. And that's a quadratic equation in x and y. It's of degree 2, defining an ellipse in the plane. Looks something like this. So this is the unit circle in this context or in this geometry. The points on here are the vectors whose quadrant is exactly 1. For example, this point here, 2, 1, is on the unit circle because if we plug x equals 2 and y equals 1 in here, let's see what we get. We'll get 4 there, so this will be 3 over 2. And we'll get a 2 times 1 here, so that'll be minus 1. So 3 over 2 minus 1, that's a half. And 1/2 y squared, if y is 1, that'll just be plus a half. So yes, indeed, we get a total of 1. So 2, 1 is on this unit circle, and so is the negative minus 2 minus 1. In fact, this ellipse has a center at 0, 0 because it doesn't have any linear term, so it's sort of centered at 0, 0. So the nature of this geometry that's induced by this dot product is closely associated with the geometry of this particular conic. The two things are very intimately connected. And so we're studying the bilinear form or quadratic form. At the same time, we're really studying the geometry of this particular conic. Okay, they are very intimately connected. Which is another reason why this approach is sort of interesting, because we are managing to look at a conic from a linear algebra point of view and basically invoking an entire geometry just by starting with the conic. Now this quadratic form really has a quadratic aspect. The bilinear form has a linear aspect. It's linear in each of the inputs. The quadratic form is quadratic. And explicitly that means that if you take the quadrants of lambda times a vector u, you multiply u by a scalar lambda, then the quadrants changes by a factor of lambda squared. Lambda squared times q of u. So it's essentially quadratic. That's why it's called a quadratic form. Geometrically, that's telling us what happens when we scale vectors. So here is that unit circle we were talking about before. These are the vectors with q of u equals 1, the unit circle in this geometry. Now if we multiplied points on here by, say, a half, that is, we're scaling by a half, then this point 2, 1 would be scaled to the point 1 half. And then this new conic, which is the scaled version of this one by just a scaling factor of half, would be defined by the equation quadrants of u equals a quarter, because a half squared is a quarter. Similarly, if we doubled this vector, multiplied it by a factor of 2 to get the point 42, then we would find that this point is on the bigger conic, which is determined by q of u equals 4. Okay, so a linear scaling in the vector corresponds to a quadratic scaling of the quadrants of that vector. Now, one of the other really essential features of such a metrical geometry is the notion of perpendicularity. The notion of perpendicularity comes immediately also from the dot product, because we define perpendicularity in terms of the dot product being 0. So the vector u is perpendicular to vector v in this geometry precisely when the dot product of u and v is the number 0. What does this explicitly mean in this context? Well, let's have a look at the situation where the vector u is fixed to be 2, 1. There it is right there. There's the vector u, 2, 1. And let's let v be arbitrary, vector xy. Then u perpendicular to v, what does it mean? Well, it means that the dot product is 0. And the dot product is given by multiplication against this symmetric matrix M. So here is u, here's the matrix M, 3/8 minus 1/4 minus 1/4 1/2, and here's the vector xy. That has to be 0. Now if we write this out, then, well, the easier thing to do is to multiply these two things first. So 2 times 3/8 minus 1/4, that's 1/8. And 2 times minus 1/4 plus 1 times 1/2, that's 0. So the product of these two is the vector 1/8, 0. And then if we just multiply that by xy, that's supposed to be 0. And what's that actually telling us? The way we multiply this vector by this transpose is it's this times this plus this times this. In other words, it's 1/8 of x equals 0. This is a linear equation in x and y. So no matter what this is in general, this is always going to be a linear equation in x and y. If you fix one of the vectors u, then the things which are perpendicular to it determine a line or a one-dimensional subspace. In this case, the subspace happens to be x equals 0. What does that look like? Well, those are just the vectors whose x component is 0. In other words, those vectors which are aiming along the y-axis. For example, this vector here, the vector 0, 1, has x coordinate 0. So it satisfies this condition. And so 0, 1 is an example of a vector which is perpendicular to 2, 1 in this geometry. And any other vector that has this property is going to be a multiple of this one. For example, 0, 2 or 0, 5/7 or 0, -3. Okay, so all the vectors in this direction are perpendicular to this vector. So we can picture that geometrically by putting a little perpendicular marking there between the vector u and this vector here. They are perpendicular in this geometry. And now let's make an observation that it appears that this particular direction happens to be the tangential direction. It appears to be that this is the tangential direction to this conic, to this unit circle, exactly at the point that we're interested in. Well, it turns out that that's a very general phenomena. It's something that we've already seen in the blue, red, and green geometries, but it turns out to be a very general phenomena, and we'll have more to say about that at a later date. I just want to alert you to this fact that, in this example at least, perpendicularity amounts to the relationship between essentially a radius vector of the unit circle and a tangential direction at that particular point to the unit circle. So that's a very nice physical interpretation. So if this was actually a true fact, and I'm telling you that it is, if you wanted to say find the vector which is perpendicular to say that vector in this geometry, say that one there, what you would do is you would just take that corresponding point on the unit circle and look at its tangent and say, aha, that's a vector which is perpendicular to this one. If you want a vector which is perpendicular, say, to this direction, you would look at that particular vector. Okay, so perpendicularity, obviously very closely connected then with the geometry of the conic, which is the unit circle. Okay, so we've talked about quadrants in this geometry. We've talked about perpendicularity. What about the other important concept of the spread between two vectors or two lines. What does that look like? How do we work with that in this more general, unfamiliar geometry? Well, the definition is the same as it always is pretty well. It's this fundamental formula. So if u is the vector AB and v happens to be CD, then the spread between the two vectors, u and v, is by definition 1 minus u dot v squared over the product of the quadrants of u times the quadrants of v. And of course, we're talking about the dot product that we're looking at. We're talking about the quadrances that we're looking at. So explicitly, in terms of AB and CD, here is u dot v, so that expression there, all squared in the numerator. And here's the quadrants of u, 3/8 a squared minus 1/2 ab plus 1/2 b squared. And here's the quadrants of v, similarly for c and d. And just as in the other kinds of situations that we've been looking at, there is a remarkable simplification or alternate form for this spread, which almost miraculously, but it's really not such a surprise, ends up involving our AD minus BC cross product term in the numerator. So we get AD minus BC squared in the numerator there, and we get on the denominator here, again, the same products of quadrances as we had up there. But in addition, we have this number here, 1/8 out front multiplying. And where did that come from? Well, that was the determinant of our matrix M. So it's really the same phenomena that we saw in the blue, red, and green geometries. We saw that in the blue geometry, there was a number 1 out here. In other words, you couldn't really see anything. But in the red and green geometries, there were minus signs here. That was because the matrices that encode those bilinear forms had determinant equal to -1. Here, our matrix has determinant 1/8. And so it turns out that there's a 1/8 in front there. And you can check that, yes, this thing here actually equals that thing there identically. Now, if you like, you could rewrite this a little bit because you could kind of clear denominators from here. If you sort of multiply top and bottom by, say, 64, 8 times 8, then you're going to get some clearing. And we can write it in a simpler kind of fashion. 8 times AD minus BC squared divided by this 3a squared minus 4ab plus 4b squared, 3c squared minus 4cd plus 4d squared. So now there's only integers. Okay, so this is a little bit onerous, but it's not that bad. Notice that it's quadratic in the numerator squared, so altogether degree 4. And down here we have a product of two quadratic expressions, so that's also of degree 4. So it has a nice homogeneous aspect that's supporting the idea that if we multiply one of these vectors by a scalar, say lambda, then the numerator and the denominator will both get multiplied by lambda squared, and there will be no net change to the spread. So the spread really is dependent on the directions of the vectors, but not actually on the vectors themselves. And it's very amenable to calculation. We can calculate with this thing very explicitly, very concretely, very directly. And now in terms of generating explicit examples, we can do that all by hand. We can do that so explicitly and concretely. We can show everybody exactly what's going on. No faking it, no infinite strings with dots here and there, no reliance on calculators to have to make obtuse calculations that in fact cannot be completed. It is a completely different story to the dominant current mind frame with regard to metrical geometry. Right? This is just a huge improvement really on the technology that we have. And as geometers get on board, they're going to see all kinds of remarkable advantages to thinking in this rational way, letting go of the irrationalities and having this beautiful rational theory emerge, which is far more powerful anyway. As demonstrated by this, here's an example, nothing special about it. We choose 3 points, say the origin for convenience, the point 2, 2, the point -3, 1, there's the 3 points. There's a triangle. We can write down quadrances and spreads. You can check the quadrances, Q1, that quadrant's there. You just take that vector and you dot it with itself using the formula. You get 59 over 8. The quadrants Q2, that vector dotted with itself, 43 over 8. The quadrants Q3, 2 dotted with itself, you get 3 over 2. There's no square roots. You don't want to take any square roots, people. Of course not, right? It's the quadrants which is fundamental. It's algebraically fundamental. It's metrically fundamental. The spreads between the segments or the sides, there's S1, there's S2, there's S3. S1 is, well, it's the formula that we've been looking at. Then you plug in the various vectors. So here's the vector 2, 2. Here's the vector minus 3, 1. You plug in exactly that formula that we just displayed. You get 128 over 129, which is pretty close to 1. So that's telling us that these two things are pretty close to being perpendicular in this geometry. The S2 spread over there, you can check that's the spread between 2, 2 and 5, 1. That's 128 over 177. And the S3 is 512 over 2,537. We're actually getting quantities here that are replacing the notion of angle. Right? You have to get your head all in knots in terms of thinking about what could an angle be in this context. And you can play various games involving cos inverse and things like that, but you don't want to. You really do not want to try to introduce angles. This is so natural and clear and direct. Here, for example, is the spread law, that S1 over Q1 equals S2 over Q2 equals S3 over Q3. These numbers are beautifully matched up so that these ratios all are exactly equal, and they turn out to be this number 1,024 over 7,611. And beautifully, all of the laws of rational trigonometry extend to this much more general kind of setting. So once you've learnt the laws of rational trigonometry, you are empowered to apply them to a much wider range of situations than you currently can. And you can start investigating all kinds of interesting things, not just over general geometries, but also over arbitrary fields, including finite fields. So our understanding, our view of geometry just dramatically increases. It's no contest, really. It's no contest. In our next video, we are going to look at the laws of rational trigonometry in such a wider context. Let's just verify that, in fact, yes, everything that we know extends, and we can expect a fully fledged, beautiful geometry mirroring most of the things that we know about Euclidean geometry, but in an unfamiliar kind of way to be working in this context. Absolutely lovely. Hope you'll join me for that. I'm J Wildberger. Thanks for listening.